Good afternoon, everyone. Welcome to Chase Plastics Chase the Knowledge webinar on Polymer Fabrication 101. This is part 4 of a 5-part series we're calling Chase Plastics 101. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. So we have a few quick housekeeping items here before we begin. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. We will answer all questions at the end of the webinar, so stay tuned. You can access and download PDF copies of this presentation, our product line card, and the information on our technical engineering team in the materials section during the presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and handouts. We would also greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website that can be found at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on processes and products specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted, including links for this 5-part series called Chase Plastics 101, where we discuss polymer basics, modification, testing, fabrication, which we're covering today, and common polymers. You can register for Part 5 on Common Polymers 101 on September 24th now. You can also watch Parts 1 through 4 or 1 through 3 as well as any previous Chase the Knowledge webinars from this page. You can subscribe or invite your coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise that she brings to the table. So without further ado, Andrea.
Hey, good morning, good afternoon. Andrea Kendrick here, going over our part 4 of our 5-part series. Today we're going to go over polymer fabrication. So part of our agenda today is going to be some brief coverings of all of these different processing methods. And so if you guys are tuning in, customer, or you have these processing equipment on your floor, probably not going to go in as deep into each of these sections as you are familiar when it comes to running your own machines, but to give a good overview, again, a good basic understanding of the different processes and then the materials or parts that are made in these different processes. So we'll go through each of those. So we're going to go over what a conversion process is. So if someone uses the term conversion process or fabrication, we're going to go over extrusion a little bit, talk about blow molding, both injection and extrusion blow molding. We'll go over rotational molding briefly. we'll talk about thermoforming a little bit. We'll take a couple slides to talk about injection molding. And at which case also, if you wanted a more in-depth injection molding presentation, we've also done a webinar on injection molding as well. And that one goes much deeper than the handful of slides I have in here today. And then we're going to talk about 3D printing a little bit. We're just going to talk about the filament 3D printing, although there are lots of other 3D printing processes that also exist. And I'll mention briefly, but we'll just talk about filament today. And then a slide on some of the considerations or the types of materials you would utilize for some of these processes. Okay, so a conversion process. So what that means, it means we're going to convert our plastic pellets or powder or granules or whatever form you're getting it in into a final part. So we take whatever is sent, again, pellets, sheet, powder, and we make a final part out of it. And so that's your conversion process. We're fabricating parts. So each of these processes are going to need something where the material will soften. And so we're going to apply heat so we can soften the material. So in this case, also note that we're talking about thermoplastics. So there might be slight differences if you're dealing with stuff like elastomers or other materials, but in this case, thermoplastics. So you'll go through applying heat. It's done either electrically, mechanically, or both. So electrically, if you're heating up the heater bands to give off the heat, mechanically would be your screw. If it's introducing some shear, it's going to heat it up that way as well. And then, or both. So in the case of something like your extrusion, your injection molding, where you've got your screw and barrel, it's introducing them both ways. So it's heating it up to soften the material so it can flow and we can start to form parts. Then we go into the forming stage. So we're going to form a part. So whether it's going to be a tube, something we're an injection mold, whatever it may be, we're going to apply pressure to form it into a part. And so pressure can be done either by squeezing it, pressing it, clamping it, injecting it into the mold, extruding it, whatever it may be. So once it is nice and soft and pliable and it's moving, we then form it with pressure. And then finally, it goes through a cooling process. So we're going to cool it back down so it hardens into the final shape, and then also allows us to handle it. Because some of these materials you have to process very hot, and so you're not wanting to grab a material that's 600 degrees coming out of the mold. It would not, your hands would not fare too well. So we allow it to cool so it can take the final shape, and then we can also handle the part out of the mold. Okay, so now we'll get into the different processes a little bit. Again, we're just kind of go through them briefly. So extrusion, as we talk about first, it's a process where you have the material that's going to run through your screw and barrel. So if you look at this picture over here, this is your hopper. It's where the material would be housed. Comes down into your screw and barrel to run through here. And then it is pushed out of the shaping die at the end. And so the shape of the die or the different dies that you might use can help make a shape that could be profile. So, and we'll show some different applications that are like that. Film, and so blown film or cast film, again, show some applications for that. Or tube, or sheet even, as we talk about thermoforming. We have to extrude a sheet first. So different shapes that will come out at the end. And this would be same kind of similar picture down here, but real world. You've got your hopper here. It would come through here, and then you have your water bath to cool whatever you're extruding out here. Now, if we compare this to other processes, a lot of them I'm going to compare to injection molding. It tends to be the pretty common one, and it's easy to compare to because generally most people understand that enough to get the comparison. So if we compare extrusion, it's a continuous process, so it keeps running as long as it's set up right. It's going to continue to run. You've got maybe cutters on the end or an additional process to crimp or to do additional stuff to it. But either way, it's a continuous process. It keeps coming out of the shaping die. You typically have lower tool and die costs compared to what you would spend for an injection molding machine or the molds for an injection molding machine. But you do have a limitation on your level of complexity for the parts. You can only get so complex. Though, to be fair, you can make some pretty complex profiles and tubes and stuff like that, just not as complex of parts as you're going to make when you injection mold parts. Okay, and so we'll get into some of the applications from the different types of extrusion. So profile extrusion. So this is where you're going to have a consistent profile as you extrude it out. So over here, if you look at the siding, you can see that this has a consistent profile done all the way through. So house siding would be done via profile extrusion, generally PVC of some sort. You'd have door seals. So this is going to be your soft materials that are used to seals in your doors. Again, same profile all the way through. Stuff like decking, if you've done something like your plastic composite decking, it would be profile extrusion. You'd also profile extrude materials that are not thermoplastics. So aluminum is extruded as well. So that'd be something here as well if you've experienced that or worked with that. Similar concept, but in this case, these would be our plastic profile extrusion parts and examples. Okay. The next we'd have tube extrusion. So the unique thing about your tube extrusion is going to be you can see that there is an opening here. And so you have a hollow opening through the middle of it. It forms a tube. So instead of a rod, which would be, you could call it rod extrusion or maybe a profile where it's just solid all the way through. Tube extrusion will have the ability to make it hollow on the inside. Maybe there's a pressurized water bath or some other way to create with the mandrel an effect and have a hollow section through it. So stuff like your hoses, be it maybe it's an outside water hose, maybe it's a catheter type hose, whatever type of hose it might be. You could use tube extrusion to create. Corrugated pipes, similar, opening through. It does go through an additional process afterwards where it then shapes kind of the outside, as you can see kind of the ridges here. So it would be an additional process to do that as well. But this would be tube extrusion. And then our ever popular straws. If you are at a place where they have the plastic straws, they would be made through tube extrusion. And so just another type of extrusion and the different products that would come from it. Then we have film extrusion, which another type of extrusion, maybe a little more unique in that it is done a little differently. It still pushes through a screw and barrel, still comes out of the die, but then kind of what happens afterwards is kind of really what affects or shapes your part. So if you've seen a blown film extrusion, you can see this piece right here through here. This is the plastic. So as it's coming out of the die, they're blowing air into it to create a larger round section of your material. Then it goes up and it is pinched off and it is rolled through and then it gets all the air out of it and then they'll perforate or they'll cut and that makes your additional parts out of it. So blown film, we'll talk about some of the applications, but stuff like your garbage bags would be made through blown film extrusion. And you have cast film, which is a different version of film extrusion, where it will come out and then it goes through calendaring rolls immediately. So this would be more of stuff like if you think more saran wrap type stuff or packaging that you can roll out. And I have pictures of that next, but a different version of film extrusion. And so grocery bags, your garbage bags, packaging films, the medical tape that they'll put around and the packaging like that, a lot of that is done through different versions of film extrusion. So a lot of different types of extrusion that are available to make a lot of different types of parts. Okay, so then we have extrusion and we add on kind of almost just like additional processing to it. So you'd go through blow molding. So extrusion blow molding is kind of what it sounds. It starts by extruding a little bit. And so in some cases, depending on the makeup of the machine or how it's formatted or what type of machine you have, it'll extrude your material through. It's called the parison. It'll extrude it through open mold halves. The molds will close around it and then air is blown into the material to have it blow out and take the shape of the mold around it. And so blow molding is a really good way to make hollow parts, though you do typically have longer cycle times than you would for injection molding. But if you need to make a big, or even sometimes they don't have to be big, but a decent size hollow part, you would use blow molding. Extrusion blow molding starts with extruding the material out, the mold clamps on it, then we blow air into it to form your part. And we have kind of a run through of that process here. So if you look over here, you have material that's being extruded out. And then you're going to have this shuttle here is going to come over and pick it up. It's going to move it back over here to where your pins here, these are your blow pins. They'll come down, blow air into it, and then it creates these little bottles right here. And so that would be kind of your process through blow molding. There's more variables and stuff like that, but in a nice simple version, material comes out, we clamp them, mold around it, blow air into it, parts move on. So extrusion blow molding. Then we have injection blow molding. So still a variation of blow molding, but instead of extruding the material out like we do for extrusion blow molding, we'll make what's called a preform first, and we do that via injection molding. And so these right here, as you can see, these are little preforms that are made. These will become bottles. So some form of a water bottle or some variant of it. So this is made in totally separate injection molding process first, and then they'll grab hold of it, heat it back up, blow air into it so it takes the shape of the mold again, and then the rest of the process remains the same. And then stuff like your ledges here, it's where it can help grab onto it so they can automate it, put it in the machine, and then blow mold it. Again, still an effective way to make hollow parts. So some blow molding parts in general, and then the next slide will kind of give you a brief rundown of your advantages and disadvantages of the two of them. But some standard blow molding parts would be your bottles. So your Coke bottles, Pepsi bottles if you prefer, water bottles, shampoo bottles. These ones look like nice generic versions of maybe the Johnson Johnson kid, bottles that you might have if you got some kids when you give them a bath. Fuel tanks, again, effective way to make hollow parts, blow molding. Okay, so then we compare them, extrusion blow molding versus injection blow molding. So again, still good process, both of them great to make hollow parts, slight differences. So with your injection blow molding, you're not going to have the pinch off. So the mold doesn't have to pinch around what's extruding out. So you're not going to have that waste. And then you don't have to trim it. So if there's an extra requirement where it doesn't fall off automatically when it pinches off, you'd have to trim it off. Or even if it does, you still might want to trim it so you don't have any flash left over. And so all that process is eliminated if you do injection blow molding instead of extrusion blow molding. You also have a little bit better control of your wall thickness because you injection mold your little preform, and that controls exactly how thick it's going to be with how much material you put in there when you injection mold it. Versus your extrusion, if you have a little bit more that comes out or a little bit less, there's going to be a little more variation potentially in your wall thickness. And so better controlled with injection blow molding, and a little bit better dimensional control of the neck area and then the threaded top. So when you do your bottles, containers, water bottles, Coke bottles, soda bottles, you have better control of the lip on it and then the threads on it as well when you do injection blow molding. Now on the flip side, you're going to end up with higher costs because, as you can imagine, you either have to pay someone to injection mold the preforms for you if you're a facility that's going to strictly do blow molding, or you have to pay to have both operations in-house. And so it costs a lot more money to injection blow mold than it would to start up extrusion blow molding. And so cost more there. And then to tell the difference, so if you've not looked or if maybe you've never really paid attention to blow molding parts or what have you, this will be a good one to go into your fridge and you pull out a mustard or ketchup bottle. If you look at the bottom, if it has a line across it, that's where it was pinched off. So that's where your molds came together and it pinched it off. That's how you can tell if a hollow part is made through extrusion blow molding. So if you have parts around you in your office sometime later today, or if you go to your kitchen to make a snack, look at some of the containers you have and look at the bottom. Again, if it's got the line, that's your parting line. It's where the molds came together, and that's where they pinched it off. Extrusion blow molding. On the flip side, if you have a water bottle like I do right next to me and you turn it over, you'll see gate marks. If there's gate mark, it's where the material came into the preform before it was blow molded. That's how you know that it was injection blow molded. So you can tell your parts, you look at hollow parts, you can tell the difference by what's on the bottom of it. And so you can tell which one's which. Okay, so that was your extrusion, then your blow molding briefly. We'll take just a couple slides to talk about rotational molding. So this is another process that you can do to make hollow parts. The nice thing about rotational molding is that you do end up with seamless parts. So you don't have the parting lines because what happens is you put a powder inside a mold, you close the mold up, it goes in an oven, and then it rotates. So as the polymer is heating up and melting, it's coating the inside of that mold, and it's taking the shape of whatever that mold happens to be. So you can see here, if I were to open this one up, you'd have this shape here, and as it's heating up, it will rotate on these different axes, and it will coat the inside, making my part. And so it's a lower cost way to make really uniform, seamless, hollow parts. Though it is quite a lengthy process. As you can imagine, it's got to use a lot of energy to warm it up, to keep it warm, and then to continue to rotate as it coats evenly the inside of the tool. So much longer cycle time than even your blow molding, or in every case, really, your injection molding. So much longer cycle. So some parts you might see that are made commonly through rotational molding would be big kayaks they'll make, or big water tankers, or kids' playground sets. So maybe the tables or some of the sets, maybe the slides. So if it's a nice hollow part that you can tell it doesn't really have seams on it, didn't necessarily come back together, it was likely rotational molded. So they'll use a powder to do that and to make these different large hollow components. Okay. All right. And then we'll talk about thermoforming. So thermoforming is kind of, it's like a secondary process really, because you do have to extrude the plastic first or buy the plastic already in sheets, because you take a sheet for thermoforming and you heat it up. So generally you'll put it kind of in a tray, or it might be automatically running through an oven of some sort to heat it up. And then once it's pliable enough and it's warm enough, it will then get stretched over or pushed down into a mold, and then they'll use either air pressure or a vacuum to get it to take shape of whatever that mold is, either the cavity or core if we're doing the inside or the outside of the part, and then it takes your desired shape. And so thermoforming, what's nice about it, it's easy to automate. In some cases, some people will, or some manufacturers will do the extruded sheet and have it do inline right into thermoforming. Or you can make the sheet first or buy the sheet first, and then it gets put into an oven made pliable, and then we thermoform the parts. Much lower pressures, lower energies. You're going to have lower tooling costs. It's in essence a little bit simpler of a process, if you will. But you do have very limited part complexity. You can only really make whatever you can sink it into, and you can't have too many additional design features into it because it will be hard to get the sheet to form into those areas. And so again, a little bit simpler of parts that can be made, but super useful parts. Thermoforming is used to make a lot of packaging. So your food packaging, packaging for stuff that you're trying to buy that's got, if it's got, it's holding your stuff in it, stuff like your K-cups, the little pods that you can get, the little coffee pods, those are thermoformed. They can make a bunch of them at one time. Solo cups are thermoformed. So if you look at it and it's kind of a nice uniform shape, like a little pod or cup or packaging, those are going to be thermoformed parts. So it starts with a sheet, goes into an oven, is pulled into a mold or stretched into a mold to make a shape for packaging or generally packaging or your cupping. But great process. You would have a lot of trimming afterwards or cutting afterwards. So there's additional processes after that that have to be done. But you can make with one sheet tons of components out of it, tons of your little pods out of it. You would just need to do the trimming and everything afterwards. Okay. And then injection molding. And so this is going to be the majority of a lot of your complex parts is going to be made through injection molding. Also, as I mentioned, if you're interested in it, we did do a separate presentation that went more in depth in injection molding. So feel free to check that one out. But injection molding in a very, very simple statement would be we melt the material in the screw and barrel. It is shot. We form the shot. We shoot it into the mold. The mold holds closed with some pressure, and it's at a cooled temperature. Cooled being the key word there. Keep it a little bit cooled so it can cool and form your part, and then it is ejected. So again, very simple form. In a couple slides, I have the actual process that I kind of briefly go through as well. But the nice thing about injection molding, although it is expensive, that's kind of its disadvantage. It is expensive for a machine. New molds are expensive. You can do aluminum tools if you're going to prototype. They cost a little bit less versus your stainless steel. They're going to cost more. But regardless, it's pricey to make new molds for it. You can use the same machine and replace just bunch of different molds, so that's convenient. But you are able to make much more complex parts. That's a huge advantage of injection molding. Also, the cycle times can be very quick. If you've got really small parts that you're running quickly, they could be anywhere from a few seconds up to, a couple minutes maybe, depending on if you're making a really large part or what have you. But generally speaking, for standard size parts, under a minute for a cycle. So pretty quick cycle compared to a lot of the other processes. And also the other thing is that the process itself, because of all the different variables, it's more complex to understand and then also to control it. So complex process, but you get to make complex parts. So that's an advantage. Okay. So if we're looking at a machine as a drawing version of it, a drawing form, if you're looking over here, this is your hopper. So you'll notice a lot of the machines start in similar fashion. They've got a hopper that houses the material, or dryer hopper if you've got one of those for a material that needs to be dried first. But that's where your material will be housed before it enters into the machine. Then it goes through a screw and barrel, so similar to an extrusion screw or barrel. The difference about your injection molding machine is you will build a shot up here, and then as you build it, it'll seat and you will plunge the material into the mold, and then you have your mold over here. And so it closes, you shoot the material in, it cools off to more solidify and then allow for handling, and then mold will open, part will eject. Okay, it's a little more complicated, few extra steps typically that are running to do this, but again, complex parts that can be made. Okay, and then again, the cycle. So you've got your mold will close, so that way you don't want to shoot the material into an open mold, then you don't form a part. It just shoots through the mold. So the mold will close, you fill it, it'll pack and hold. Then you have your cooling time and recovery, meaning that we're building the next shot so we can continue the process and have it be hopefully fully automated. It keeps going. Then your mold opens after it's been cooled and the part ejects, and then we start all over again. So not a continuous process like extrusion where it just kind of keeps coming out, but it can be fully automated. So and automatic. So it'll just keep running if you have a good cycle going. So again, complex process, complex parts. So some of the parts here would be stuff like your toothbrush. A lot of the components of that are going to be injection molded. And then if you have the simple ones or even the non-simple ones that have the grips on them, those then go through a secondary process or potentially done in the same mold, depending. But over molding, if you've heard that term, it'll over mold it with a soft touch material. You can do that with injection molding. A lot of different components within a lens are going to be injection molded. So you get the whole lens that would be injection molded, the housing for it that would be injection molded, gears, connectors. So you can see that the way that even just they look a lot more complex than some of the other components that we're making. So lenses, you look around if it's made with plastic and you can see little ejector pin lines or a gate or what have you, a lot of parts are made through injection molding. Okay. And then the last process I'm going to go over just briefly, again, as I noted, there are tons of other 3D printing options available. So maybe you're an injection molding house or an extrusion house or any manufacturer really, and you want to make an ergonomic handle or you want to make a fixture or you want to prototype a part and you don't want to go as far as to make a prototype aluminum tool or anything like that. 3D printing is a potential option. We call it FFF. This is fused filament fabrication. You might have heard FDM. That's a trademark term. And so we don't use that on our presentations, but they mean the same thing. So I'm using filament and it is extruded layer by layer. And then the layers are, the material's warm. So they adhere to one another. And so layer by layer, I build up a part. And so you can see here, in the process of building one, and kind of near the end of building this one. So layer by layer, I'm basically stacking my filament that's being extruded out to form a part. Your costs are much lower. Some of these really non-complex 3D printing machines you can get for a couple $100. And then you can go as super high-end ones that have to run super high temperatures that cost hundreds of thousands of dollars. But on a very simple lower end of it, you can spend a couple $100 and have a decent 3D printer to start running some of these. And then the other disadvantage here would be that you have limitations for your materials. So not every material likes to attach to the layer. The layers don't like to adhere together. So you have some materials that aren't really good for it. Soft touch materials generally are not super great for filament 3D printing either. They're just a little harder to feed through the machines. So they can be a little more difficult to 3D print. And so you have issues there. And then the other issue would be is if you're doing it for a prototype tool, it's really more for a look and feel because the strength of the layers is not going to be nearly what you would get with an actual injection molded part. And so if you're trying to do any type of testing or anything, it's not super easy to do that because it's not going to have the strength that an injection molded part will have. But for to look at it or to see how it will fit or what it will look like or how it will work, you could do that. We're just not necessarily going to test it because it's not going to perform as well as an injection molded part. So a good option there. So some parts, I mean, if you've got some kids in high school, they've got their own machines and they're making all sorts of fun little items. You can make, again, up here kind of concept designs for different gears. If you need to make a certain handle, if you need to replace a small little part that doesn't need super stringent performance, you could make that. all sorts of different little options that can be done with 3D printing, which is convenient. All right, so talked about our different processes. We talked about some of the different parts that could be made with them in nice, simple format. So now let's talk just a little bit about the materials, what are common and what type of material you'll tend to use. So if we go back to extrusion or extrusion blow molding, these types of materials are going to need high melt strength. So when you're extruding it down or extruding it to the side, so down for your extrusion blow molding, you saw in the picture it's extruding down. Other extrusion processes, it's extruding typically out, so more horizontal. It has to be able to hold its own weight. So if you go to extrude it out and then it doesn't have any strength there, it's just going to break apart. And then you can't have a continuous process if it's breaking. So these materials will have to have high melt strength. And so you typically end up with a material with high molecular weight. You got a lot of chain entanglement, and so it holds itself really well. And that then also correlates typically with a really low melt flow, because your lower melt flows then correspond to a higher molecular weight, higher melt strength. And so materials anywhere from polyethylene, so we have a standard 2 melt polyethylene that could be extruded, and then going all the way up to PEEK. So maybe we're making rod stock out of PEEK, and then it can be machined into different components. And so huge option and variable range for materials for extrusion all over the place. Rotational molding, as we mentioned, it's a powdered resin that you use. And so you're either going to use a material that's already in powdered form, or you can use a resin that can be then ground down into powder. So the most common materials for this is polyethylene. They use that one most commonly. You can use other materials, and they have been used and are successfully used. Polyethylene and the commodities tend to be just the more common ones for this process. Again, it's got to be in powder form or ground down into a powder form. Then thermoforming, as we mentioned, because it's kind of your secondary operation, you have to have extruded sheets first. These are going to typically come in unfilled variants. So you're not going to use a filled material for these because it's going to be really difficult to form or to get it into a shape if you've got really stiff glass in the material. So unfilled products, the most common of these ones are going to be your commodities. So your polyethylenes, your polypropylenes, your polystyrenes. These are going to be your most common materials that are used in those applications. Again, you need them in sheet form. So you've either extruded the sheet yourself or you buy the sheet to be thermoformed. Then injection molding, like extrusion, huge range, anywhere from your commodities all the way up to your high-end materials, cell phones, PEIs, run the gambit. Just depends on what you're making and what you need the material to be doing. That'll kind of dictate what material we're going to use. But in these cases, we typically use a higher melt flow material. We want a little bit less of the chain entanglement. We want it to flow a little easier, and we don't want to have to utilize a ton of extra high pressure to get the material to flow. So generally use a little bit higher melt flow materials within the same range of options. So we want to make sure we fill the cavities, and then within the materials, depending on if you're making one large one cavity part, or if you're making a 32 cavity and they're small parts. Well, we need the material to fill all the way out there. So we likely use an even higher melt flow for the ones that are high cavitation. So a good range across the board for injection molding in terms of our material. Generally higher flow though. And then lastly would be your filament. And so of course we're using filament because they have to fuse together. As I mentioned, some of them don't feed well and some of them don't like to layer upon each other super well. So that limits our material options. And the most common one that you're going to find or you're going to buy most commonly is going to be PLA. That's what they use most commonly for filament in all bunch of different colors. But then they've got some specialty nylons. They've got specialty nylons that have, certain fiber fillings, and then you get all sorts of crazy materials as long as they can get the layers to adhere to one another. The materials can be used. But if you go and you buy your couple $100 machine and then you buy a spool of your filament, generally if it's just a common everyday material, it's going to be PLA. So that'd be your material for that. Okay. And with that, that is what I had for our brief overview of our different processes.
Great. Thank you, Andrea, for your comprehensive presentation. At this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. We have Jason Merkel, Technical Manager, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinars, and we welcome your feedback. Also, Please be sure to check out our webinars page at chaseplastics.com/webinars for past webinar recordings that you can watch at any time and future webinar announcements in registration. If you would like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself. And Jason, I'm going to hand it over to you for questions, but I don't see any in the questions bar yet, so you might be off the hook today.
No problem. I'll see if any trickle in before we part ways.
Andrea, did you have any afterthoughts you wanted to add?
I don't think so. Generally, we have the questions that lead us into further conversations typically, but
Oh, there you
sounds
go.
like, and a lot of people I'm sure that tuned in are, they're doing some of these fabrication processes, so they're pretty familiar generally. But nice to delve into maybe some that they don't have at their facility that
We
they
did
don't
have
know
one.
as much about.
Yeah. First question is, this particular customer works in injection molding. In their facility, they use both hydraulic and electric molding machines. Question is, do all molding processes use both, or are some more common in certain molding practices?
Sure. It's more of a preference. So they have their unique advantages and disadvantages. So stuff like your hydraulic machines, you can tend to get larger shots. They have a little bit more power, but they tend to be a little bit messier because you've got hydraulic oil that you have to deal with. And then they're louder for that reason, versus your electric that maybe not as powerful, but they're a little bit quieter, a little bit cleaner. So it really comes down to a preference. Certain countries also have a huger preference. So if you find that you're working more with Japanese end users, they're pretty particular for and care for your electric ones. And then you have other ones. The other thing is also cost. Hydraulic machines typically cost less. So if you're starting up and you're buying a machine, if you don't need the quiet or the clean or what have you, you're probably going to start with the lower cost hydraulic options. But it really comes down to preference. It comes down to what you're trying to do and what they prefer. Generally, you find a company or a brand that works really well for you and you tend to stick with it. And that's what we tend to see. You've got one company that tends to have, 20, 30 of the same type of machine because it has worked really well for them in the past and they tend to stick with that.
Awesome. Got a few more now, Andrea.
Okay.
Can you briefly explain a bit about compression molding and how it differs from thermoforming?
Sure. So compression molding, instead of taking a sheet and making it pliable and then having it form down into the mold or have the mold come up into it, compression molding will use more of like your granules, and they'll use high temperature and pressure to basically smush the granules together to form a part. So it would be similar to automating it, but you use different starting material and you use pressure and temperature versus using temperature and then kind of more of like a vacuum. So not as much pressures or energy for your thermoforming, and you'd make slightly different parts with it.
Yeah, I would say just to add to Andrea's points, and she covered it. I mean, if you want to really draw a firm line in the sand, generally speaking, thermoforming is a relatively low pressure process. The molds aren't, being clamped together under high tonnage in most cases. And you're using vacuum and sometimes positive pressure to help with movement of a sheet that is almost molten, at least softened. In the case of compression molding, to Andrea's point, you're really high pressure forcing, solid and sometimes liquid components together to form a product. So more of a high pressure jam it in there with compression molding and lower pressure shaping of a softened product with thermoforming. Thermoforming tends to be, thin as well, almost exclusively, to have relatively thin walled products, where compression molding can give you a lot more variety to do thicker walled solid body type components. Next question, Andrea. Since injection molding requires high flow resins to properly fill cavities, how do engineers balance material selection between flow rate and mechanical strength, especially when designing for thin wall or complex parts?
Yeah, good question. Feels like maybe a couple questions within there. So there's a few things to go about answering that. So starting with thin wall. So if you're making really thin wall parts, you're going to be limited on the material choice at that point because some materials can't flow into as thin of sections because they don't flow as well. They don't shear thin as well as other materials. So materials like a polycarbonate, it's not going to flow into as thin of a section as you could get something like a nylon 6/6 or 4/6 into because it doesn't thin out as well. And so you try to shove it with a ton of pressure and it's not going to want to flow through there. And so your thin wall comes down to how thin you're trying to get, and then what materials you could use for those thin wall of applications. Or if you're starting with an application at regular, maybe what we'd consider more of a regular or nominal thickness, and then we want to design it thinner, we'd have to make sure that the material has the capability to do that. So that would be one. And then on the flip side of that, within the material, so let's say we stuck with polycarbonate and that's the material we're going to use, trying to figure out between melt flow and performance, there will be some trade-offs. So stuff like polycarbonate specifically is a great example. When you go really high melt flow, you end up losing some of your mechanical performance, some of your impact performance. So the super high flow PC grades, you're going to lose some of that impact. If your component doesn't need that, or it's not going to see impact and we're not so concerned about that, then that ends up being okay. And we're okay to lose some of that. If it's a component that is going to see it, or we might drop it, or it's going to be in some application where that could be a problem, okay, well, then we're going to have to figure out some way to use a lower flow. So maybe depending on how it's designed, maybe we need to open gates a little bit more, let the material flow a little bit better. Maybe we try a little bit higher temperatures as long as we don't go so far as to burn the material. Try that. There's a few ways to try it, but it is a good delicate balance. And so it's why we try, or we would like to be able to be part of conversations in the beginning to understand what you're trying to do. And then the other part of that comes down to, from a commercial standpoint, well, how many cavities are you going to make now? So if you have to make so many parts for the year, does it make sense to have higher cavitation? And do you have a material that can handle that and flow and fill all of those cavities? Or is it something where maybe more than one tool has to be made? And it's those conversations that you would have in the beginning to figure out the capabilities of the material that you're looking to use to help make some of those decisions.
I think, to further, answer the question, we love to have these kind of conversations with customers when possible, especially early as on in the design phase, to still be able maybe to influence design or material selection before it's too late. Because it's not only about moldability, right? To your point, there's mechanical strength needs that's can be affected by obviously wall stock and flow length, but also sometimes you give up properties moving from a low flow to a high flow resin. Andrea mentioned the example of polycarbonate. If you look at the impact values of a 8 melt polycarbonate compared to a 30 melt or a high end 65 melt, which we use for like light pipes and things like that, they have very, very different mechanical properties. So when we're comparing different options for use, understanding potential trade-offs for tensile strength, elongation, impact resistance, things like that are all important to take into consideration at that point, because there might be other products that can fill the tool and do so without any modifications to said tooling, but are you giving something up in part performance also needs to be considered. So if you got any similar situations you'd like to discuss offline, we'd welcome that opportunity. What appears to be the last question here, Andrea. This customer has a specific printer that they're using for 3D printing, a K1 Max Reality, where they recently had filament clogging the X of the printer, changing the material, changing the material a lot as well as the guide tube between the cogs and the I guess I'm not understanding the question here. looking to figure out why changing the material fixed the problem basically with clogging.
Sure. Do we know, was it a change in material type or just a different filament spool of the same material? I don't know if it mentioned that in the question.
No, unfortunately. So,
Okay.
Anthony, if you want to reply with more information here, that'd be great. Otherwise, we'd be happy to take your question offline. There's a few things that could go into it. If it's the same material, two different lots, then we'd want to, take a look at what type of material it is. If
hmm
it's moving from one polymer to another, then there might be a different rhetoric as to why one worked over another. So,
It looks like he just replied it was a spool,
oh,
Different spool.
different spool
different
lot.
spool.
Okay,
Yeah.
gotcha.
hmm
Thanks.
Yeah. So troubleshooting 3D printing is not necessarily what we'd consider our expertise, but it could be something along the lines of that particular filament could have had some rough, I don't really want to call it rough edges, but it could have been a rougher spool. And so that could have been getting caught on stuff or getting stuck. That could have caused it. If it's a material that has to be dried, because some people will utilize nylon filament, if one came in a little with more moisture than another, there could be a few different things that could be causing that. Um, but it could just be the quality of the filament on the spool that was causing an issue.
All right, that looks like all of our questions for today. So we would like to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We do hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in September.